All right. So we are going to do our last lesson on induction, and we are going to talk about induction and Fibonacci numbers, which is just a very common type of induction problem. So get yourself ready for notes, and we are going to look at this set of problems. So a reminder of what the Fibonacci numbers are. So this is a sequence. You might remember it goes 1, 1, 2, 3, 5, 8, 13, and so on. And the idea here is that it is a sequence. Remember, a sequence is just a list of number where the sum of the previous two terms equals the next term. So we start with nothing, 1, another 1. 1 plus 1 is 2, 1 plus 2 is 3, 2 plus 3 is 5, 3 plus 5 is 8, 5 plus 8 is 13. The next term would be 8 plus 13, which is 21, and so on. Now, the way we write this mathematically is we say that if capital F sub n is equal to the nth Fibonacci, whoop, gotta focus on spelling, Fibonacci number, and that means that f of 1 equals 1, f sub 2 is equal to 1, and f of n minus 1 plus f of n is equal to the next term, f of n plus 1. So this is the rigorous mathematical definition of the Fibonacci sequence. Now, prove that f of n plus 1 squared, so this term squared, minus f of n plus 1 times f of n, so the term behind it, minus f of n squared is equal to a power of negative 1. Now, as I said, we're going to use induction for this. So we're always going to start with that first idea, and we're going to say that n is equal to 1. So that means f of 2 squared plus f of 1 times mixing terms around. N plus 1 is 2. 1 minus 1. So this, using the rigorous definition here, we know that f1 is 1 and f2 is 1. So 1 squared minus 1 times 1 minus 1. And the question is this equal to negative 1 to the first? Because n equals 1. Well, this is 1 minus 1 minus 1, which is indeed negative 1. So we know it's true for n equals 1. So then again, we are going to say our assumption statement. We assume that it's true for some n equals k. So we know f k plus 1 squared plus, why do I keep saying plus? Oh my goodness. Minus f of k plus 1 f k minus f of k squared is equal to negative 1 to the k for some k in the natural numbers. And always important to remember what we want. We want to show that this is true for k plus 1. So f k plus 2 squared minus f of k plus 2, f of k plus 1 minus f of k plus 1 squared is equal to negative 1 k plus 1, right? So it's true for k plus n equals k plus 1. So in this case, and what's going to be helpful for a lot of these Fibonacci problems is when I start the third step, because you're not looking at a long series here, you're not adding on a term. I'm just going to ask you to consider this statement we want. So f of k plus 2 minus k plus 2, k plus 1 k plus 1 squared. So just consider this statement. And what we're going to do is show that this is true to this. So we're just starting with here. And I'm going to use the Fibonacci expansion here. Say f of k plus 2 is k, f of k plus 1. Because these would be the consecutive terms before. So this is factored. You consider it factor there. Squared. And I'll factor it again here. K plus f of k plus 1. And then the other two terms I'm going to just leave as is. Now, when I expand this all out, and I'm going to write noticeably smaller for this next line, I'm going to say, well, this is fk squared plus 2 f of k plus 1 f of k plus fk plus 1 squared minus fk plus 1 f of k minus fk plus 1 squared minus f of k plus 1 squared. So we're just using the nice distributive property there. So now what I'm going to do is I see some like terms that I can cancel out. First of all, I see that I can cancel out one of these f of k plus 1s and subtract away there. So we just have one left. I also can cancel out one of the fk plus 1 squareds. So we have two of them. We can cancel one of them out. So then I'm left with fk squared plus fk plus 1 fk minus f of k plus 1 squared. Now, if we consider, we knew this statement to be true. This is true. Well, if you look here, you'll notice that those have the same terms, but we're looking at a different order. So I'm going to reorder it. And using the transitive property, these are all equal. So then this is negative f of k plus 1 squared plus fk plus 1 fk plus fk squared. Right? I'm just reordering. Now, and this is why it's helpful to write out what we know, is, oh, well, this first term was positive here, and the other two were negative. So I'm going to factor out a negative 1. Negative 1 fk plus 1 squared minus fk plus 1 f of k minus fk squared. Well, now this here, we know what that equals. That's negative 1 to the k. So now we have negative 1 times negative 1 to the k. Oh, look, that's same base. That's negative 1 to the k plus 1. Using the transitive property, these two are now equal, and we know that this is true for n equals 1 and any consecutive number k plus 1. Therefore, it must be true for all the Fibonacci numbers that this difference is equal to a power of negative 1. So this is going to be the important idea, and here's a new idea that I think is helpful in terms of induction, is that it's not necessarily always a series, but sometimes you are considering the one you're looking for and then end up substituting back in. If you have questions about this presentation problem here or any of the three others, please be in touch, and